Hello, all current and future JoinerCAD users. We have some good news for you, inspired by JoinerCAD users. Many thanks to them for this. So let us waste no time and see what I'm talking about here. We have developed and implemented a new feature that makes it easy and fast to place hardware elements, to control them when needed, and to update the model when geometry changes. With the model update, the state of the embedded components will automatically update depending on the operating logic. All you need to do is to create the desired hardware element, insert it into the assembly, select the panels to be connected, and select the placement settings. Before we start creating a component, we need to get familiar with the logic of operation. I will take as an example the connection of two panels, where one of the panels rests on the side of the other panel. I will use Rafix S20 connectors to connect them. When two panels are joined together, the area of contact between them can be called the contact area. This area has a relative contact area length and contact area width. Accordingly, this contact area can be matched with the coordinate system, which is aligned with the X and Y axes respectively. These values are important because I will use them to design my hardware elements. The concepts of contact area and coordinate system are fundamental to the new smart hardware components, as they are the core of their operation. As I mentioned earlier, the coordinate system is very important, so I match it with the ViewCube coordinate system, which is available in the Fusion 360 software environment. When I create a sketch of the contact area, I will draw it in the corresponding coordinate plane. I create a new sketch in the XY plane. I draw a rectangle whose geometric center is the same as the world coordinate system. I call up the dialog window and create two user parameters, contact area length and contact area width. I set them to relative values of 600 millimeters and 20 millimeters. These values will be automatically changed by the system during insertion, so the values given are only for the initial creation and management of the contact area. I would also like to point out that both of these parameters and the other parameters that will be used in the settings later in the video are marked as favorites. This way, we can access them in the JoinerCAD plugin dialogs. The created settings are assigned to the rectangle. I rename the created sketch to Contact Area for later access. In addition, I enter some other parameters that are needed for control or calculations, that is, offset 1 and offset 2, which control the distance of the edge elements. The spacing between them is called placing length, and the maximum distance between the two components is called max distance. There may be more or less parameters depending on the hardware component being described and the sizes that we need or want to control. I will create a new sketch that will be in the same XY plane and at one of the ends, I will draw a relative circle of 1 mm diameter to represent the location of the first Rafix S20 component. I call up the parameters dialog again and add additional values. First, the Y coordinate. Second, the user offset 1 and user offset 2 values, which I will be able to control via the control form. And third, the offset 1 and offset 2 values, which I will use in the calculations. I will temporarily treat these offset values as user offset values. I add the dimensions, assigning the entered parameters accordingly. Although not necessary, I draw the center of the position of the second outermost Rafix S20 element. It will only be used for the visual representation in this case, as I will control the positions of the Rafix S20 elements with other values. I stretch the first circle of the sketch in the position direction of the Z-axis by 10 millimeters. In this case, the solid body created will only be used as a starting point for the checks and for the insertion of the Rafix joint. I call up the parameters dialog and add some other values. That is, placing length, which can be expressed as a formula by subtracting the values of user offset 1 and user offset 2 from the total length of the contact area length. I will enter the min distance and max distance values. By changing these values, the user can define the minimum and maximum distance between the components. These values will be needed for further calculations. Once we have the min and max distance values, then the offset values can be calculated. For this, I will use the following formula in the offset 1 parameter. If placing length is greater than or equal to min distance, then the user offset 1 value is used. Otherwise, contact area length is divided by 2. This will ensure that if the distance between the components is greater than the minimum, then the user offset 1 value is used. If the distance is smaller, then only one Rafix S20 component will be inserted and placed in the middle of the contact area. I will do the same with offset 2. If placing length is greater than or equal to min distance, then the user offset 2 value is used. Otherwise, offset 2 is equal to the value of offset 1. I create the number of intervals parameter. This parameter uses the ceiling function. It rounds the resulting value to the higher integer. In this case, the formula will look like this: ceil of placing length divided by max distance. This value will allow us to calculate the number of spaces between the different components. Note that this value must be dimensionless, so the unit of measurement is chosen to be no units. A new parameter, number of components, is created. This value is without measurement units. I will use the following formula for its calculation. If placing length is greater than min distance, then I will add 1 to number of intervals. Otherwise, when the size is smaller, this value will be 1. I add the last parameter, space between. This value will calculate the space between the components. For this, I use the following function. If placing length is greater than or equal to min distance, then the parameter placing length is divided by number of intervals. Otherwise, the value is 0. Using the rectangular pattern command, I will multiply the drawn pin in the grid. I specify the distribution type, spacing, and the quantity parameter, number of components. Finally, I specify the spacing parameter, space between. Before inserting the imported Rafix S20 components, I perform a check to make sure that the components are placed where they are supposed to be, and that the logic created and mapped to the parameters is working as I expect it to. I call up the parameter management dialog. When I change the contact area length to 400 millimeters, I check that the number of components is reduced to 2. If I change the size to 900 millimeters, I check if the number of components increases. In this case, I can say that the logic is working fine when reducing and increasing the number of components. With a length of 100 millimeters, I check the condition where placing length is less than min distance. In this case, the number of components must be reduced to 1. This is exactly what happens. The created file is saved. In this step, I will use the template I created to insert the geometry of the CAD model downloaded from the manufacturer. I should mention that in the example I've shown, the model is static and does not adapt according to the dimensions of the panels. However, the components in our smart hardware library have more complex control logic. New examples with smart hardware components have been added to the installation of the new version of JoinerCAD. One of them is the Rafix S20 connector and the connecting pin. Old users can download the new examples from our GitHub repository, the link to which you can find in the description of this video. I will insert the geometry of the connecting pin into the template file. Using the Joint command, I attach the geometry of the pin to the geometry of the solid body I drew earlier. I use the Break Links command to break all links to the original file. Similarly, I insert the Rafix S20 connector, position it, and break the links to the original file. In order for the components to be used in the Sculpt command, I will add the Sculpt geometry. I create a connecting pin component, draw a sketch of the hole, and stretch the sketch using the Extrude command. I ask the command to create a new body. I expand the tree, find the solid bodies of the connecting pin, and rename them bolt and hole, respectively. I assign the attribute subtractive to the hole body and neutral to the bolt. In this case, the whole geometry will perform the sculpting operations, and the bolt will not react to these operations. I turn off the visibility of the hole because we don't need to see it in the model. I activate the Rafix S20 connector component, add the whole geometry again, assign attributes, and deactivate the whole visibility. You can find more details about how the Sculpt operation works, what solid bodies and their functions are, in our other videos. Their links are provided in the description of this video. Using the rectangular pattern command again, I create a grid of components using the same number of components and space between parameters. Only this time, I choose Components for multiplication and select the components of the Rafix X20 connector instead of solid bodies. As before, I will check whether the Rafix S20 element I have created will change accordingly as the values change. I call up the Parameters dialog, change the value of Contact Area Length, and check how this element behaves. In order to keep the components in place after multiplication with the rectangular pattern command, I use the rigid group command and bind them together. In order for the components to be correctly accounted for in the BOM environment, they need to be given the appropriate attributes. I call up the BOM management command on each component by clicking the right mouse button and assign the part number, also known as code and description values. Accordingly, I define these components to be countable in units. That is, I give the status quantitative. You can see more details about what the statuses are and how they work in our previous videos, the links to which you will find in the description of this video. The assembly must be given the status translucent. In this case, the BOM analyzer will ignore the level of this assembly and read only the values of quantitative elements. Before using a component in compounds, the created parameters must be linked to system values. In addition, users can add descriptions and images if required, which will be displayed during insertion. I call up the Map Parameters command. In the window that appears, I specify which type of connection is used, panel connection. I map the length to contact area length and the width to contact area width. Other values can also be linked to the parameters if required. The system will insert the calculated values from the model into the specified parameters during insertion. I switch to the Direction tab. Here I can specify, if necessary, whether a direction is mandatory for the component. This may be relevant when the component has to be oriented specifically to some plane. I switch to the Parameters tab. Here I can add parameters that I want to use or control during insertion, or change after the component is inserted. The Add Parameter command inserts a parameter, and the Add Value command allows to give multiple values to the specified parameter. I am opening a two-panel assembly into which I will insert the Rafix S20 component I created. Using the Hardware Attachment command, I select and insert the Rafix S20 component. Finally, I specify the panels to be connected and the direction. After clicking OK, the Rafix component is placed. I open the Parameters dialog and widen the panels. As can be seen, Rafix S20 no longer corresponds to the changed situation. I press the Hardware Refresh button, the situation is recalculated, and the Rafix quantities and positions are adjusted. I call up the Change Parameters dialog and specify the Smart Hardware component. The system reads the parameters that can be changed so the user can make corrections. That's what I'm doing, changing the distance from the edge. The system updates the calculations and adjusts the placement of the components. The work is finished. You can start designing your own components, or you can take a closer look at our examples. Good luck!